Optical phenomena. Optical phenomena are any observable events that result from the interaction of light and matter. A mirage is an example of an optical phenomenon. Common optical phenomena are often due to the interaction of light from the sun or moon with the atmosphere, clouds, water, dust, and other particulates. One common example is the rainbow, when light from the sun is reflected and refracted by water droplets. Optical phenomena, ito yung mga napapansin natin mga pangyayari na resulta ng interaction ng light at ng matter. Ang isang halimbawa niyan is mirage. Ang mirage ay kadalasan natin nakikita sa disyerto.
Hello there, this is Shankaran and with me is Pooja.
Hi.
And we are back with a concept of physics for you, and for that I want you all to look very carefully at the road. Can you see that?
It seems like we are driving in a river.
And you look carefully, as you're going closer, layer by layer is actually disappearing. There goes a layer.
Right.
And see the next layer, right? This is amazing, right? Don't you feel we should understand how exactly this happens? And for that, my friend here Pooja is going to take you to a desert.
So, are you guys ready? Now, seeing water on a highway is one thing. But imagine a thirsty traveler traveling in a desert, he sees water. There is nothing more miserable than that, right? Let's understand why this happens. Basically what happens is, during day the land becomes hot. Because of that, the air molecules above are warm. But as you go up, it keeps on becoming cooler and cooler. That means, right now at this level, if I hold my hand like this, I can clearly see the difference. That is, my lower hand is much more warmer in comparison to the above hand, which is much more cooler. So what we have understood is the layer at the bottom is more warmer, but as you go up, it gradually keeps on becoming cooler and cooler. Now, the light from the sun hits the object. The tree there is the object. After hitting the object, the light will reflect and it will enter the first layer. Now, the first layer is denser. Now, as and when the light is going from denser to rarer, it will keep on bending away from the normal. So, at each layer, what you see is the light is bending away from the normal. But at one point, what you will notice is light will hit at an angle which is greater than critical angle. And at that point, instead of light undergoing refraction, the light will undergo total internal reflection and enter my eye. Now, once it enters my eye, human eye always perceives that light always travels in a straight line. So now I can see the reflection there at the bottom. So the reflection of the tree is there. Similarly, the reflection of the cloud is also seen there, and that appears like water. So that is how mirage takes place. So let's summarize the key points. For mirage to occur, there has to be total internal reflection. And for total internal reflection, there has to be two conditions that needs to be fulfilled. The first one is light should always enter from denser medium to rarer medium. And the second condition is very simple. Light should hit at an angle which is greater than critical angle. So here are some amazing mirages that happen in nature.
How are rainbows formed? Nabubuo ang rainbow kapag ang sunlight ay scattered from raindrops into the eye of an observer. Kadalasan ng raindrops ay spherical shape rather than teardrop. Ang spherical sa Tagalog ay pabilog, bilugan o bilog. Basta circle, ganon. So dahil dito sa shape na to, kaya natin nakikita yung rainbow.
basic wave equation. So dito may papanoorin kami sa inyong video which is madali lang and pakitandaan na lang dahil may mga question kami kukunin.
In the previous video, we described waves using their wavelength lambda, which is the distance between crests. Their frequency f is how many waves the source makes per second, and is the same as the number of waves that pass by a point each second. The speed v is how fast each wave crest moves. It's also the distance each crest moves per second. The cool thing is that we can now use the frequency and wavelength to work out the speed of the wave. Here's how. Let's choose a wave with a 2 Hz frequency and a 3 meter wavelength. Speed means distance divided by time. So the easiest method is to see how far the wave travels in 1 second. Then the speed will be that distance per second. How many wavelengths will it travel in a second? Let's see. That was 1 second. Let's try it again. The wave moved 2 wavelengths in 1 second. That makes sense because 2 Hz means 2 waves per second. So the wave must have moved ahead by 2 wavelengths. Each wavelength is 3 meters long, so it travelled 6 meters altogether. The speed must be 6 meters divided by 1 second, or 6 meters per second. Notice that the frequency 2 Hz multiplied by the wavelength 3 meters also gives the same answer. Six. Is this a coincidence? Maybe not, because in 1 second all waves must move a distance of the number of waves made, which is their frequency, times the length of each wave, which is their wavelength, equaling their speed. In this case, we got the right numerical answer for speed, 6. But how can hertz multiplied by meters give meters per second? Remember, frequency in hertz means the number of waves per second. And wavelength is how many meters long is each wave, or meters per wave. Well, the 2 times 3 gives 6. Now look at the units. The waves on the top can cancel with the waves on the bottom, leaving only meters on the top and seconds on the bottom, or meters per second. So when we multiply the frequency in hertz by the wavelength in meters, we do get the speed in meters per second. Sweet. But this is just one example. Would multiplying frequency and wavelength work for other waves too? Let's try a frequency of 3 Hz and a wavelength of 4 meters. How far will the wave crests move in 1 second this time? Well, 3 Hertz means that there will be 3 waves, and each will be 4 meters long. So 12 meters altogether. So the speed must be 12 meters divided by 1 second, or 12 meters per second. But we could have skipped to the answer by just multiplying the frequency by the wavelength. 3 Hertz by 4 meters. It worked again. But what if we had chosen a time period of 2 seconds instead? Wouldn't that change our answers? Let's see. The frequency is 3 waves per second, so in 2 seconds, 6 waves will be made, each 4 meters long. The crests move 24 meters in 2 seconds, or 12 meters per second. Same answer. Even though we doubled the time, we also doubled the distance that the wave travelled. So their ratio, which is the speed, stays the same. Multiplying the frequency by the wavelength always gives us the speed of a wave. Whether it's a water wave, sound wave, or light wave.
So ayan. The next one is the wave theory of light. To explain the origin of colors, in 1635 to 703, Robert Hooke developed a pulse theory and compared the spreading of light to that of waves in water in his 1665 work Micrography. So dito, para mas mapadali, ipinaliwanag ang pinagmula ng colors. Si Robert Hooke ay gumawa or bumuo ng isang teorya or bumuo siya ng isang theory or sinasabi dito, the theory of pulse. At dito, ikinumpara ang pag-spread ng lights sa waves dun sa water. In his 1665 work, Micrography. When you say Micrography, it is physiological description of minute bodies. It is made by magnifying glasses. So yeah, ito yung observation niya is 9. The next one in 1672, Hooke suggested that light's vibrations could be perpendicular to the direction of propagations. So ito, kapag tatandaan natin na pagsabi ng 1672, Hooke suggested that light's vibration. So sinabi ni Hooke na ang pag-vibrate ng lights ay pwedeng perpendicular. Pag sinabing perpendicular, it is the relationship between two lines which meet in a right angle or intersect to the direction of propagation. So the next one is this one is the 1622 to 1695. Christian Huygens proposed that light was emitted in all directions as a series of waves in a medium called the luminiferous ether. So ayan, ito ang laging tatanda natin. When you say luminiferous, it is the light bearing. And the ether is the substance which permits space but does not provide any mechanical resistance. So, dahil ang wave ay hindi or the wave ay hindi apektado ng gravity, it was assumed that they slow down upon entering a denser medium. So, yeah, sabi nga, as waves are not affected by gravity, Sinasabi dito na hindi apektado ng gravity. It was assumed lang that they slow down upon the entering a denser medium. And then the next one is the wave theory predicted that light waves could interfere with each other like sound waves. And dito, sinabi dito sa wave theory that predicted that light waves could interfere. So, sinabing maaaring makaapekto sa bawat isa like ng sound waves and the the light waves and the light waves and the sound waves. So dito, light waves, sa madaling salita, light waves and sound waves could be interfere in each other. So possible na pwedeng makaapekto sa dalawa ang could niya interfere nga, 'di ba sabi? So, yan. Pwede makaapekto sa bawat isa. The next one is another supporter of the wave theory was Leonard Euler. He argued in Nova Theoria Lucis et Colorum in 746 that diffraction could more easily be explained by a wave theory. So dito, si Leonard Euler, siya yung isa pang taga-supporter of the wave theory. Sabi nga dito, he argued in a Nova Theoria Lucis et Colorum. So, dito, in 746, pag sinabi kasing diffraction, it is bending of light around the object. That's why mas madali siyang i-explain or ipaliwanag by wave theory. So, yon. The next one, in 1816, Andre Marie Ampère gave Augustin Jean Fresnel an idea that the polarization of light can be explained by the wave theory if light were a transverse wave. So yan, in 1816, yan, binigyan ni Andre Marie Ampère si Augustin Jean Fresnel ng isang idea that polarization ng light could be explained sa pamamagitan ng wave theory, and if the light were transverse wave. So, ayan. The next is Simeon Denis Poisson added to Fresnel's mathematical work to produce a convincing argument in favor of the wave theory, helping to overturn Newton's corpuscular theory. So dito, si Simeon Denis Poisson added to Fresnel's mathematical work upang makagawa ng isang kapanipaniwalang argument in favor of the wave theory. So yan. So, sabi dito nga, yun, sabi nga ni Simeon Denis Poisson added to Fresnel's mathematical work, so parang nagkaisa sila or something ganon. So, parang nagtulungan sila na ipabagsak yung theory ni Newton, which is yung corpuscular theory. So, yan. The next one is the weakness of the wave theory was that light waves, like sound waves, would need a medium of transmission. So yan, the weakness of the wave theory was that light waves, katulad din ng sound waves, would need a medium for transmission. So when you say transmission, the process by which light energy is transmitted. So, yun lang. Next.
Corpuscular theory of light. Sa corpuscular theory, sinasabi na ang light daw ay gawa sa maliliit na particles na tinatawag na corpuscles na lagi nagtatravel sa straight line. Ang light daw ay form of energy na lagi nagtatravel from one place to another place at high velocity. Madaming scientists na nag-attempt na ipaliwanag ang nature of light. Pero si Sir Isaac Newton ang kauna-una nag-attempt na ipaliwanag ito. Noong 17th century, may dalawang theories tungkol sa nature of light ang na-propose. Yung isa yung wave theory at yung isa naman ay yung corpuscular theory. Ang corpuscular theory ay kadalasan tinutukoy na or tinatawag na particle theory or Newton's theory of light. Pero katagalan na-abandon ang theory ito dahil sa wave theory.
Newton's corpuscular theory of light states the following. Light consists of corpuscles, which are a stream of discrete, tiny, light, and perfectly elastic particles. Every luminous source, like the sun, a lamp, or a candle, emits these corpuscles. These corpuscles travel in straight lines in all possible directions. The rate at which these corpuscles travel may differ depending on the medium in which they disperse. The vision of human beings is a consequence of these corpuscles falling on the retina of the eyes. Various colors of light are due to the difference in sizes of these corpuscles. These corpuscles could perfectly explain the concepts of reflection and refraction of light. The reflection of light, which consisted of corpuscles, is just like the reflection of a perfectly elastic ball. Consider the case of a perfectly elastic ball that hits the wall, which is a rigid plane. When this ball hits the wall normally, it bounces back and travels along the same path that it takes during the throw. However, when this ball is thrown at an angle to the wall, it bounces back and away from the wall at an equal angle with respect to the normal. However, it takes the opposite direction. The angle of incidence, I, of the ball is equal to the angle of reflection, r. Reflection of corpuscles of light follows the same rules that reflection of this perfectly elastic ball exhibits. In other words, each of the corpuscles behaves just like an elastic ball. This means that when corpuscles hit the surface normally, they travel along the same way back, and when they hit the surface at an angle, they are repelled near the surface and reflected back such that the angle of incidence, I, is equal to the angle of reflection, r. According to Newton, the refraction of light was due to the supposed change in the speed at which they travel, thereby causing a resultant change in the direction whenever these corpuscles enter from, say, a denser medium to a rarer medium. Although Newton's corpuscular theory of light could successfully explain the reflection of light, his assumption of higher velocity of light in denser medium as compared to the rarer medium has been disproved. He was also unable to validate his supposition that various colors of light are due to the difference in sizes of these corpuscles. For these reasons, the hypothesis was rendered baseless. The biggest limitation of Newton's corpuscular theory of light was that it could not illuminate the phenomena of interference, diffraction, and polarization of light. This is why the theory was later abandoned in favor of Huygens' wave theory of light, which proved that the light travels in the form of waves.
Electromagnetic theory of light. Ang teoryeng ito is pinangunahan ni Michael Faraday noong 1845. Siya ay nakadiskubre ng magnetic field influence polarized light. So, sa pagdiskubre niya ito is, may nakita siyang piece of glass na, ewan ko, pinag-experimentan niya o nakalagay lang talaga dyan. Tapos may light source na dumaan doon sa piece of glass na yon. Then, lumabas yung light, syempre nag-reflect. So, all of a sudden, nag-rotate yung salamin. Then, yung lumalabas na light, galing doon sa salamin is para nag-dim or nag-change yung o nabawasan yung light beam. So, example nito is yung polarized glasses na nakikita natin na sinesale sa SM o kung saan man ganun. Diba kapag sinuot natin yung polarized glass na yun is nagka-cancel out siya ng beam kapag tumingin tayo sa liwanag ng araw. Or kahit yung tinatry natin sa stall, yung salamin nila may image pala na nandun. So, yung effect kasi ng polarized glasses na yun is ganito. Ayan. Kung makikita natin yung light beam, siya yung source, yung light na nagmumula doon is unpolarized light. Kumbaga, kalat-kalat pa yung liwanag niya, nasa all over the place. Tapos, dumaan siya sa isang filter, horizontal filter. Yan yung tinatawag na polarizer. Kumbaga, yan yung salamin mismo nung yung binibenta. Kumbaga, yan yung piece of glass ni Faraday. Then, after dumaan ng light source na yan doon sa filter is Naging polarized light siya. Bakit? Kasi na-cancel out niya yung ibang kalat-kalat na light. Kung makikita nyo rito sa vertical lines ng polarizer, after diba makikita natin doon sa unpolarized is may mga horizontal lights. So, na-cancel out yun ng polarizer, kaya yung lumabas na light is polarized light na. Ganon. So, kumbaga nag-cancel out siya ng beam. Next. So, after ng mga ginawa ni Faraday, yung discovery niya, na-inspire dito si Maxwell na aralin yung electromagnetic radiation and light. So, dito na pumapasok yung radios, yung UV rays, infrared, microwaves, ganon. Ito yung tinatawag natin electromagnetic spectrum. Kumbaga parang dito nakasukat yung frequency, energy, tsaka yung wavelength. Naka-organize sila. So kapag mas mahaba yung wavelength, mas mababa yung frequency niya, tsaka energy. Kaya kung mapapansin natin sa mga movies, yung kapag nagkaroon ng tawag dun, yung sumabog na malakas, kalimutan ko yung tawag, na nagka-cancel out siya ng iba't ibang electronics. So, radio lang yung kadalasan nagagamit nila. Kadalasan sa mga apocalypse, ganun. Radio lang yung nagagamit nila kasi mas mababa yung frequency nito, tsaka hindi siya sa signal towers na kadepend. So, kapag mas mababa naman yung wavelength, mas higher yung frequency niya, tsaka mas mataas din yung energy. So, kadalasan dito is hindi na siya safe sa atin. Hindi na safe sa balat natin. Ganun. Ayan, yung UV lights, yung gamma ray, yung X-ray. Pero kapag yung light ng X-ray na yun is direktang dumikit sa balat natin, syempre, delikado na rin sa atin yan. So, yung makikita natin diyang visible lights, yung rainbow color, yan yung nakikita ng mata natin. So, sumunod naman is, sinubukan ni Heinrich Hertz yung mga theory ni Maxwell at naging successful naman yung mga experiment niya kasi nakita niya yung radio waves na sinasabi ni Maxwell is nagbe-behave siya exactly katulad ng visible light. Yung mga nakikita nating light, ganun. Ganun nagta-travel yung radio waves. So dahil din dito sa mga experiment ni Hertz, doon na natin napag-aaralan yung reflection, refraction, diffraction, and interference. Marami pa iba. So dahil din dito sa mga theory ni Maxwell tsaka yung mga experiment ni Hertz, doon na nag-improve yung technology natin. Doon natin nakabuo ng radios, yung television, mga cellphones natin, ganun, towers. And kumbaga yung mga experiment ni Hertz, kung ano man basa doon. Kumbaga yun yung nag-prove sa theory ni Maxwell.
Electromagnetic waves are known to possess the following properties. 1. They are produced by accelerated or oscillating charge. 2. They do not require any material or medium for propagation. And number 3, they travel in free space at the speed of 3 × 10 raised to the 8th power meter per second. The following prominent scientists made a significant contribution in resolving how electromagnetic waves behave. Let's start with James Clerk Maxwell, an English scientist who developed a scientific theory to better explain electromagnetic waves. Maxwell used this field theory to assume that light was an electromagnetic wave and then correctly deduced the finite velocity of light. It was a powerful logical argument for the existence of the electromagnetic force field. He noticed that electric fields and magnetic fields can couple together to form electromagnetic waves. Maxwell discovered that a changing magnetic field will induce a changing electric field and vice versa. Heinrich Hertz, a German physicist, applied Maxwell's theories to the production and reception of radio waves. The unit of frequency of a radio wave 1 cycle per second is named Hertz in honor of him. He proved the existence of radio waves in the late 1880s. He used 2 rods that served as a receiver and a spark gap as the receiving antennae. Where the waves were picked up, a corresponding spark would jump. Hertz showed in his experiments that these signals possessed all of the properties of electromagnetic waves. Next, we have Michael Faraday, best known for his discovery of electromagnetic induction. He was responsible for introducing the concept in physics which describes electromagnetic interaction. But perhaps it is not so well known that he had also made fundamental contributions to the electromagnetic theory of light. André-Marie Ampère made the revolutionary discovery that a wire carrying electric current can attract or repel another wire next to it that's also carrying electric current. The attraction is magnetic, but no magnets are necessary for the effect to be seen. He went on to formulate Ampere's law of electromagnetism and produced the best definition of electric current during his time. We also have Hans Christian Ørsted, a Danish physicist and chemist who discovered that the electric current in a wire can deflect a magnetized compass needle, a phenomenon which was rapidly recognized and which inspired the development of electromagnetic theory.
Quantum theory of light. The quantum theory of light as proposed by Albert Einstein states that light travels in bundles of energy and each bundle is known a photon. Photon is a type of elementary particle. It is a quantum of the electromagnetic field, and photons are massless, so they also move at the speed of light in vacuum. The photon theory of light stems from Planck's quantum hypothesis and was confirmed using the photoelectric effect experiment. Through physical experiments, Planck demonstrated that energy is in certain situation can exhibit characteristics of physical matter. Quantum theory tells us that both light and matter consist of tiny particles which have wave-like properties associated with them. Light is composed of particles called photons, and matter is composed of particles called electrons, protons, and neutrons. In 1905, Albert Einstein provided an explanation of the photoelectric effect, an experiment that the wave theory of light failed to explain. And he explained that the exact weight that electrons are rejected from a metal surface when the light hits the surface. He did so by postulating the existence of photons, quanta of light energy with particulate qualities. In the photoelectric effect, it was observed that shining a light on certain metals would lead to an electric current in a circuit. Photoelectric effect is the emission of electrons when electromagnetic radiation such as light hits a material. So quantum theory of light, tells about the both light and matter consists of tiny particles.
The existence of black holes was predicted by Einstein's theory of general relativity, which states that matter warps space and time, creating what we call gravity. The theory also predicts that when two black holes collide, they send out ripples through the fabric of space-time called gravitational waves. These ripples were first detected in 2015 by an incredibly sensitive experiment called LIGO, proving Einstein right. Then in 2019 we managed to photograph a black hole for the first time. On the picture we can see a bright ring of material circling the black hole itself, which is silhouetted in the centre. If you're unfortunate enough to get sucked into a black hole, it would be devastating but also pretty spectacular. As you circle the drain of this cosmic plug hole, all the photons being pulled alongside you would create a stream of blinding light, and the stars would begin to distort and bend. Then a looming darkness would wash over you. Any further and you'll cross the event horizon, the line where the gravity of the black hole is too strong to resist. You wouldn't just be crushed, but your body would be pulled apart at different speeds, resulting in what physicists delightfully call spaghettification. Once you're inside the black hole, it gets a bit harder to work out what happens. General relativity's equations fail catastrophically at the centre of the black hole, called the singularity. This is where quantum theory comes into play, but quantum theory and general relativity don't really get along. General relativity says when matter falls into a black hole, information is destroyed, but quantum mechanics says that can't happen. We need a unified theory to reconcile the two.
Speed of light. The speed of light is vacuum is 186,282 miles per second or 299,792 kilometers per second. And in theory, nothing can travel faster than light. In miles per hour, light speed is a lot about 670,616,629 miles per hour. If you could travel at the speed of light, you could go around the Earth 7.5 times in 1 second.
Refraction of light. So, sa refraction of light is nagbe-bend ka ng light dito. So, sa refraction of light is malaking impact ang change in speed. Kumbaga parang mula sa rarer na medium o sa hiwa-hiwalay na molecules, bigla siyang mapupunta sa denser medium, katulad ng water, yung dikit-dikit yung molecules. So, dito sa refraction of light, dito nagmula yung telescopes, microscopes, peepholes of house doors, cameras, yung mga lens ng cameras, tsaka movie projectors, and magnifying glasses. So, katulad nga sinabi ko kanina, yung refraction of light is pagbebend nagbe-bend yung light ray. So, makikita natin dito is yung incident ray is nasa substance 1, which is yung rarer medium, kaya ito yung air. Kasi yung air is hindi dikit-dikit yung molecules. Then, yung incident ray is pumasok siya sa boundary ng substance 2 or yung denser medium, which is sabihin natin yung water. Kasi yung molecules ng water is dikit-dikit. Kaya doon bumabagal yung speed ng light. Dahil, di ba, katulad nga sa atin, di ba, kapag tumatakbo tayo sa land, ang bilis-bilis natin. Pero kapag pumunta na tayo sa water, ang bagal na natin. Sa reflection kasi, ang angle of incidence tsaka yung angle of reflection is iisa lang. Pero dito sa refraction of light, ang angle of incidence tsaka ang angle of refraction is magkaiba. Mas malawak ang angle of incidence kaysa sa angle of refraction. At yung babasehan natin dito is yung normal line. So, itong handle ng kutsarang to, ito yung incident ray. Kumbaga, buong kutsara nga yan yung incident ray. So, yung kutsara is nasa substance 1. So, pumasok siya sa substance 2, which is yung water. Kaya bumagal yung speed ng light. Kaya aakalain natin na lumaki yung image ng kutsara, pero hindi. Bumagal pala yung speed of light. Kaya mas nakita natin siya ng clear. So, ito naman yung dalawang lenses, ang concave and convex. So, ito yung mga nakikita, yung mga salamin na ginagamit sa telescope, ganun sa cameras, yung katulad ng kanina, yung sinabi ko kanina. So, sa concave naman is dito nagsispread ng light outwards. Kumbaga, nilalabas niya yung ilaw, kinakalat niya yung ilaw. So, kapag pumasok yung light sa convex, lalabas siya ng parang iisa na lang yung beam. Iisang direction na lang ng light yung makikita natin. Kasi sa hugis pala malalaman na natin kung bakit eh. Yung concave, nakakurba siya palabas. So, yung light, lalabas siya ng pakalat. Then sa convex naman, yung lens ng convex is naka-curve paloob. So, yung mga light is may ipon yung light sa gitna, kaya doon na lumalabas yung light na iisang beam na lang siya. So, ito yung dalawang examples na napili ko dyan. Ang best example sa concave is yung flashlight. Ayan na, nakikita na natin, nag-spread out yung light sa flashlight dahil sa tulong ng concave. Nakatulong yung concave sa pagkalat ng light rays. Dito naman sa convex is yung magnifying glass. Siguro isa pang example sa magnifying glass is yung kapag tinapat natin siya sa sunlight, tapos may papel tayo, and then nakikita natin nag-aapoy siya. Sa tulong yan ng convex lens kasi iniipon niya yung light ray na maging isang beam. So lahat ng init ng araw is nagtipon-tipon doon sa loob ng convex at nilabas naman ng lens as isang beam na lang. Kaya yung heat na yon nakatulong sa pagsunog ng papel. Kaya ito rin, makikita rin natin dito sa picture na lumapit yung letter sa atin kasi yung light, yung epekto ng convex lens. Ay, ito sa paggamit ng magnifying glass, hindi mo siya ididikit sa mata mo. Ididikit mo siya doon sa libro mismo ng yung libro mismo o yung kung ano man yung binabasa mo. Sa internal reflection, malaking bagay ang angle. And sa internal reflection, hindi mangyayari ang internal reflection kapag hindi siya dumaan ng refraction. Katulad ng nakikita natin dito sa image. Dito sa first image, nakita natin na refraction angle siya. The next naman, pumunta siya ng boundary or hindi naman siya boundary. Kumbaga, ito na yung critical line. Yung critical line is dito nagtatapos yung angle ng refraction. Then next naman is dito na naganap yung total internal reflection. Kasi ang 'di ba ang reflection nagaganap siya dito sa medium 1 o dito sa substance 1 naka letter V. So dito naman sa total internal reflection is naka letter V siya pero nandun na siya sa medium 2. Ibig sabihin nasa dense medium na siya. Doon na siya nag-bend. Kaya tinatawag siyang total internal reflection kasi nandun na siya sa loob ng denser medium. So next naman, ito yung example natin. Makikita natin yung laser beam dito is nasa ilalim siya. So ibig sabihin, nandito siya sa angle ng denser medium. Then makikita natin tong line na to. Ito ang critical line o yung line kung saan nagtatapos ang refraction angle. Then bigla namang bumaba yung angle dahil nag-reflect siya doon sa critical line or umikot na siya. Kaya nag-reflect yung light beam doon sa boundary at naging internal reflection. Kung matatandaan natin kanina ang sa law of reflection, di ba? Normal ang basehan natin. Itong normal na to sa gitna kung saan nag-bend. Ang angle of incidence at ang angle of reflection is iisa lang. So dito sa total internal reflection, iisa lang ang angle of incidence tsaka angle of reflection.
Light attenuation. Light attenuation is important parameter from determine the photic zone, which is the zone with sufficient light from photosynthesis and thus relevant from total parameter product, as well as the distribution between pelagic and benthic primary product. So, sa madaling salita, ito ay tumutukoy sa mga pagbawas ng intensity nito through a medium due to absorpting. Sa madaling salita, ito ay tumutukoy sa pagbawas ng intensity nito through a medium due to absorb. So, pag sinabing absorption, it's the process or ito ang isang proseso by which light is taken by the substance or skirting of proton cores with sunlight is deflected. Ito ay dahilan or pagbabago ng isang direksyon after tamaan ng isang bagay.
Emission of light. In physics, emission is the process by which a higher energy quantum mechanical state of a particle becomes converted to a lower one through the emission of a photon, resulting in the production of light. The frequency of light emitted is a function of the energy of the transition. Since energy must be conserved, the energy difference between the two states equals the energy carried off by the position. The energy states of the transitions can lead to emissions over a very large range of frequency. For example, visible light is emitted by the coupling of electronic states in atoms and molecules. Then, the phenomenon is called fluorescence or phosphorescence. On the other hand, nuclear shell transition can emit high-energy gamma rays while nuclear spin transition emit low-energy radio waves. For example, nanonood ka ng fireworks, paano nagagawa yung light or colors na nakikita natin? So, yung way paano nagre-release ng energy ang isang atom in the form of light is pag yung electron na-excite or nasa excited stage, tatalon siya to a higher energy level. Kaya lang, in reality, ang gusto talaga ng atom ay ground state lamang. So, definitely, babalik ulit sa pagiging ground state. Yung pagbalik niya sa ground state, kailangan may i-release siyang energy. Yung energy na yun na ilalabas, yun yung in the form of light or electromagnetic radiation. Pag sinabi naman natin ground state, yun yung electron configuration ng isang atom at the lowest energy level possible.
Interference. Two light waves of the same wavelength can interact under appropriate circumstances so as to reinforce each other if they are in phase or to cancel each other if they are out of phase. Sinasabi dito ng dalawang magkaparehas na wavelength ay pwedeng maging isa or pwedeng maging together, ganun. Tapos kapag naman to reinforce each other if they are in phase or to cancel, parang yung liwanag ng wavelength or yung kapag naubos yun, ewan ko, next na lang. If a beam of light falls on a thin film, such an oil slick on puddle water, part of the beam is reflected from front of the oil film and part from the back. Sinasabi naman dito, yung liwanag ng beam is kapag bumanda ito sa oil on a puddle water, parang magre-reflect ito sa front ng oil film and part from the back depending on the thickness of the film. The two reflected beams can reinforce or cancel. And when monochromatic light falls on a film of varying thickness, a series of dark and light bands known as interference fringe is produced. With white light, the sequence of overlapping light and dark bands from the spectral colors leads to Newton's colors. The film appears black or gray where it iris thinness and the light waves cancel. As it becomes progressively thicker, it appears white, then yellow, orange, red, violet, blue, green, yellow, orange, red, violet, and so on. Newton's color can also be seen in cracks in glass or in crystal, in a soap bubble, and in anti-reflection coatings such as on camera lenses. Sa madaling salita, kapag ang wave ay nag-reflect from inner and outer surface, so dito nagmimit at nagsama-sama na na-defend sa bawat isa or hindi, sama-sama sama-sama na ma-defende ata. Defende? Maka-apekto or makagambala sa bawat isa at dito tinatanggal or inaalis ang ilang part ng white light by destructive or constructive interference. Kaya nagkakaroon or nagpo-produce ng panibagong color.
Early scientists, unable to perceive light's motion, thought it must travel instantaneously over time. However, measurements of the motion of this wave-like particles become more and more precise, thanks to the work of Albert Einstein and others. We now understand light speed to be a theoretical limit. Light speed, a constant called c, is thought to be not achievable by anything with mass, for reasons explained below. That doesn't stop sci-fi writers and even some very serious scientists from imagining alternative theories that would allow for some awful past trips around the universe.
Atmospheric optics. It is a collective name from everything having to do with light and color in the atmosphere, which includes subjects on the ground. Atmospheric optics is such as rainbows, halos, glories, and many other visual spectacles produced by light. It deals with how the unique optical properties of the Earth's atmosphere cause a wide range of spectacular optical phenomena. Optical phenomena are any observable events that results from interaction of light and matter. Again, interaction of light and matter. One is the common example is the rainbow. When light is from the sun, it is reflected and refracted by water droplets.